My name is Ashley Alfred, and this project is peak identification using KS test and probability distributions. The subject base for this project is chromatography, which is a technique for separating the chemical components of a mixture using a device called a chromatogram. Peak shape is a characteristic signature of the identity of an analyte, so there is a unique normalized peak shape for each analyte. Given some data, one could normalize peak shapes and then compare those shapes with unknown analytes to determine if the analytes are a match and the goodness of the match. And you can judge that by several methods such as R-squared values and absolute percent error. This project looks at the KS test, Kolmogorov-Smirnov, and probability distributions. So the KS test is it's a test that determines whether two arbitrary distributions are the same, and I use this in MATLAB. All of the coding is done in MATLAB. So typically in MATLAB, when you run a KS test on two samples, it gives you a test statistic and a p-value. But for my data, I didn't get p-values. I didn't get the proper p-values for my results. And so I was looking for a way to assign a p-value for comparing the analytes. And the way that I did that is by running the KS test and using the KS test statistic for all of the times that I ran, and I was able to create data sets from those and then fit a distribution to them. So a quick explanation of the data. The data has 11 analytes, ran at two different concentrations 3 times. So I have 1 microgram per milliliter and 20 micrograms per milliliter. So I first applied the KS test, comparing each analyte to itself from each data column, and that gave me 22 data points. Then I compared them, each analyte, with all other analytes from one data column, and that resulted in 55 data points. And so the comparing analytes to multiple measurements of themselves followed a Weibull distribution with a null hypothesis that the analytes are the same profile, that is H1. The second data set, comparing the analytes to each other, followed a normal distribution with a null hypothesis that the analytes are different profiles, that is H2. And so if we look at the data visuals, we see hypothesis 1 and hypothesis 2, and I'll just use an example to show how to read it. So if I look at A1 versus A2, it gives me a KS value of 0.259. So looking at this chart, the probability of the KS value being greater than 0.25, I would conclude that it is the same profile with the sureness of, I would be 1.6% sure that it is the same profile. So, which is, I'm not very sure. So I would in fact conclude that A1 and A2 are different. So looking at the conclusion that we have so far, for KS values that are greater than 0.175, we created this rule that we would reject H1. And so using the data set where we have 55 data points, when we compared each analyte to all the other, we ran this rule with those data points, and there's a 70.9% of those 55 data points correctly reject H1. And then we also created the rule for KS greater than 0.108 accepting H2. We have 98% of the analyte comparisons correctly accepting H2. And so I just included another one just to show how to read it. But we did this for this whole thing for one concentration, and then we did it for an increased concentration to see how the percentages differ. So you see parentheses 20, 63.6%. So we were looking at the behavior of two different concentrations. So for our future work, we would like to test more data and maybe look at chemical behaviors of analytes with incorrect conclusions. So our goal was to be able to assign up p-values, and so we have completed the first part of our goal. So I would like to thank Dr. Pranendu Das Gupta from the chemistry department and Dr. Sue, my advisor, from the math department. Thank you.